All right, welcome back. We're taking day 2 video notes on our gas laws. We talked about pressure and temperature. Today we're going to look at how some of these on volume and how these are officially related. We're going to start with Boyle's law. Boyle's law goes through and states that when you have a sample of gas, it occupies a certain volume and has pressure, and the temperature is constant, so temperatures are control. If we vary either pressure or volume, they are inversely related. So what that means is we can set up an equation like this: P1V1 equals P2V2. And what that means is that you have your same sample of gas. For example, if you were to take the syringe, you had that sample of gas contained. When you change the volume by moving the plunger back and forth, it's the same sample of gas, you're just changing the volume, the pressure changes. And what we see is that, so this is the pressure 1, the initial pressure, initial volume. If you change either the pressure or volume to a new number, you're going to get a new number for the other one. And this is saying that they're inversely. So if we take P1 and we pressurize it, so we increase pressure, what this is saying is that the volume will decrease, and vice versa. So our two constants, our controls, temperature and moles, we're not changing those. We see pressure up, volume goes down. Or if we decrease the pressure, volume goes up. So that's that inverse relationship. They go in opposite directions. Make sure when you're doing your calculations, all your pressure variables have the same unit and your volume. So if you have atmospheres for pressure, you can't have millimeters of mercury in the other one. They have to be exactly the same. Same thing with volume. Liters and liters, milliliters, milliliters, whatever your volume unit is, it needs to be the same. So let's do a couple of examples. We're going to start with this one, and it's one in your notes. A helium-filled balloon contains 125 milliliters of gas at a pressure of 0.974 atmospheres. What volume will the gas occupy at standard pressure? So you're going to start getting more complicated word problems like this, and you're going to need to start to be able to kind of differentiate the variables. So we have a helium-filled balloon. It contains 125 milliliters of gas. So now we have to find the pressure that goes along with that volume. And if you look over here, 0.974 atmospheres is what is said to have been in with that volume. All right, and then they're asking for what volume. Let's do this differently. What volume at standard pressure? And if you remember from the last video, standard pressure is 1 atmosphere. So let's go ahead and pull our variables out. There's our equation. So we got P1 as 0.974 atmospheres, and to go with that, we had the 125 milliliters. So what do we have for the second set of variables? P2 is 1 atmosphere. That's that standard pressure, and V2 is what they're asking for. So we go through, plug it all into our handy-dandy equation. So here is P1 times V1 equals P2, and V2 is our unknown. And then you just simply need to solve it. Multiply these two together. You're going to divide by 1 atmosphere, but it's 1 atmosphere, so it's going to be okay. And you notice, since we have atmospheres on both sides, those are going to cancel out. And we will be left with milliliters, which is 122. 3/6 to go with our measurement. Okay, next. There's a couple more examples that are not in your notes. So at this point, what you could do is go ahead and just pause the video and try it on your own. You don't have to write them down if you don't want to, just for the extra practice. So pause now and try it on your own. All right, let's go through the solution. So we have gas occupying 526 milliliters at a pressure of STP. That's standard pressure. When the pressure is changed, the volume becomes 376. And you should be asking yourself, if the volume is now 376, why? What is going on? If it's getting smaller, that must mean it's being pressurized. So we can go through, and when we do our volume, it should be small, or our pressure, it should be larger. So let's go ahead, pull out our variables. P1 was 1 atmosphere because of standard pressure to go with the 526. P2 is, we don't know, they're asking about it. and V2 was the 376. So plugging it into our handy-dandy equation, P1 V1 equals P2 V2, you get 1 atmosphere times 526 equals P2 times 376. Multiply and divide correctly, and you should get a pressure of 1.40 atmospheres with 3 seconds. We have one more extra example if you'd like. So I would encourage you to try it on your own. All right, here we go. High altitude balloon contains 3 liters of helium gas at 103 kilopascals. What is the volume when the balloon rises to an altitude where the pressure is only 25 kPa? So we have 3 liters of gas under 103 kPa. We're reducing the pressure. You would expect it logically, so the pressure is what's keeping the balloon this shape. If we reduce the pressure on the outside of the balloon, we expect the balloon to get larger. So you can think about it logically and check your answer. P1, 103, V1, 3. And then we go through. P2 is 25, and now they're asking for that new volume. So hopefully when we solve for it, it's going to make sense. Plugging it all into the handy-dandy equation, multiplying and dividing correctly, we get a volume of 12.4 liters, and that totally makes sense. It's 4 times as big as the 3, and that makes sense because this is 4 times smaller than the 103 kPa. So you can check your work logically that way. All right, that's one of 2 laws we're talking about today. Let's go ahead and move into Charles's law. This was another one we investigated a little bit with our lab. And Charles's law states that when you're looking at volume and temperature at constant pressure, they're going to vary directly. And we have an equation, V1 over T1 equals V2 over T2. It is fractions, but it's not hard to solve when we go through that process. We're keeping pressure and moles constant. So if we were to go through and increase temperature, let's say we keep the pressure constant, we would expect our balloon to get larger. So that's a direct relationship. If we decrease temperature, our molecules are going to start slowing down, and if they're slowing down, they're not moving as fast. They can occupy a smaller volume to keep the pressure the same. And just like with Boyle's law, whatever you're doing with these, they all have to have the same units. Charles, sorry, had to do it. Okay, let's do our example. This is the one that's in your notes. A sample of neon gas has a volume of 752 milliliters at 25 degrees Celsius. What will be the volume at 100 degrees Celsius? So we're looking here, and we see a couple of things. Let's do the highlighter, it makes it easier. So we have the 752 milliliters, and it's really easy to see that that goes with the 25 degrees Celsius. This is the way it's worded. So this volume at 25 degrees Celsius. So now we need to figure out what volume, so now we have a new volume we're finding, what we have at 100 degrees Celsius. I color-coded them to make sure that we can see that those are the 2 different sets of variables. All right, so our V1 is 752, P1 25, oh yes, don't forget you have to convert to Kelvin. If you leave it in Celsius, you will get the wrong answer every single time. So how did I get the 298? Remember from our last video, you simply add 273 and you get 298 Kelvin. V2 is what they're asking for. What will the volume be at 100 degrees Celsius? And what are we going to do with 100 degrees Celsius? Convert to Kelvin. So we'll go ahead, add 273, and that's easy peasy, is 373 Kelvin. Now that we have all our variables out, let's go ahead and set it up with our equation, V1 over T1 equals V2 over T2. So there's our V1, and we just have to make sure we put the correct temperature to go with that, and it's going to be the Kelvin temperature, the 298, and that's going to be equal to our V2, which we don't know, over 373. And then you can go through, and many students at this point, there's multiple ways to attack this mathematically. Probably the easiest way is just to cross multiply. That's what I tend to encourage students to do. So you'll do V2 times 298 and then these two, and you end up with this linear form, which is easier for us to understand. So you get, there's the multiplication of V2 and 298, and then the 752 and 373. So now we have these numbers. All we need to do is divide by 298 to get V2 by itself. And so when we do that, it'll look like this. And it looks messy because there's lots of units. It's a fraction, but it's really not a big deal. But notice when we do that, what we can cancel are our Kelvin units. Ooh, we like that. And then we're going to be left with just milliliters for our volume. So that's nice. 3 sig figs in our final answer, and you should get 941 milliliters. Now, does that answer make sense? If we are going from 25 degrees Celsius up to 100, does it make sense that our volume increased? Absolutely, because our molecules are moving faster and faster and faster, and so they're pushing and pushing and expanding. Alrighty. 2 examples, extra examples for you to try on your own, and then we're done. Oh no, 1. I did 1 for sure. So this one, now we have a helium-filled balloon, and it has a volume of 2.75 liters at 20 degrees Celsius. The volume of the balloon decreases to 2.46 after it's placed outside on a cold day. What is the outside temperature in Kelvin and in Celsius? So at this point, this is when you would pause. That way you can try it on your own first, pulling out your variables and solving. Okay, so I'm going to go through, pull out my variables. 2.75 liters at 20 degrees Celsius, but I'm adding 273 to that in order to get the 293 right there. Let's get rid of this. To get the 293 Kelvin. And then they tell me the V2 decreased to 2.46, and they want me to figure out how cold it is outside in Kelvin and in Celsius. Alright, handy dandy equation again. Just plugging in what you know. 2.75 liters over 293 Kelvin is equal to my 2.46 over T2. I don't know T2. And this one tends to get students a little bit more frustrated because even though it's just math, students see a variable in a denominator and it gets a little craziness. Let me bring that back for a second. I think I come to work. So the idea is, here we go, there we go. Again, just cross multiply. So I'm going to take that and multiply it by T2, 2.46, multiply it by 293. And you can get that variable out of the denominator easy peasy. And so now we have it the exact same linear format, much easier for us to solve visually as well. So you go through and you'll take the 246 times 293 divided by 275. And what we can do once again when we set it all up is we can now cancel our units. So the liters cancel. And now we're left with just Kelvin. So that's awesome. Our answer will be in Kelvin. Makes it easy. And so we get 262 Kelvin. And ask yourself, does that make sense? 262 compared to 293? Absolutely makes sense. It got colder, and that's why our volume shrunk. So the last part of this, to make sure you put it into Celsius as well. So just subtracting your 273, and it's negative 11 outside. That balloon got cold. All right, that's it. We're all done with Boyle's and Charles' law. Thank you very much, and good luck.